Picture this for a second. You're out for a run, and your foot strikes the pavement. Or maybe you're at the gym, right? And you're landing a box jump.
Oh, yeah, or even just, stepping off a slightly too high curb while you're crossing the street.
Exactly. And you feel that impact in your feet, your ankles, your knees. That shock wave traveling up your legs is, well, it's totally expected.
Yeah.
But have you ever actually stopped to think about what is happening inside your abdomen at that exact millisecond?
I mean, probably not, right? It's this phenomenal biomechanical event that we just completely take for granted. We tend to focus almost entirely on the external architecture.
Like the bones and joints.
Right, the bones and joints, while totally ignoring the soft tissue matrix that's actually holding our internal anatomy together during those moments of, intense deceleration.
Well, that is our exact mission for this deep dive. We are going to unpack exactly how high-impact landing movements physically stretch, strain, and sometimes permanently alter our internal structural tissues.
It's such an important topic.
It really is. And for you listening, we're pulling together this really fascinating mix of sources today. We've got biomechanical motion capture research, some deep molecular biology focusing on pelvic connective tissue, and specialized physical therapy protocol.
And to really grasp what happens during a landing, I mean, we have to look at the anatomy that's actually catching the fall.
Right.
Your internal organs, so the bladder, the uterus, the bowels, they aren't just floating freely in a void in there. They are suspended and supported by a highly complex, really dynamic hammock at the base of your pelvis.
Like a literal web of tissue, right?
Yeah, exactly. It's this web of muscles, fascia, and tendon-like structures. And every single time gravity brings you back down to Earth, that internal hammock has to catch the falling weight of all your visceral organs.
So to understand how those specific tissues stretch, we need to first look at the sheer physics of the impact itself. And in our sources, there was this fascinating motion capture study from the CDC.
Oh, I love this study. Right. It's so cool. They measured something called intra-abdominal pressure, or IAP, during a 30-centimeter box drop.
And what's particularly illuminating about that study is how they actually isolated the generation of internal pressure into a four-element model.
Okay, wait, what are the four elements again?
So you have gravity, acceleration, abdominal muscle contraction, and breathing. All four of those interact dynamically to create the pressure environment inside your core.
Right, got it.
But when they mapped the exact sequence of the jump, the data revealed something incredibly counterintuitive about the flight phase.
Right, because during the jump, there's this distinct phase where you are essentially in free fall. You've stepped off the box, but your feet haven't hit the ground yet.
Yeah, you're airborne.
And during that split second, the acceleration at your hips and the actual pressure inside your abdomen, it decreases significantly.
It's wild. Your internal organs are essentially weightless for a fraction of a second.
But then comes the moment of ground contact. Yes. At that exact millisecond, there is a violent, massive spike in both hip acceleration and intra-abdominal pressure.
Just a huge surge.
Massive. It's a phenomenon driven by the momentum transfer of the abdominal viscera. Because think about it. Your skeletal system stops moving downward because it hits the floor.
But your organs don't.
Right. Your organs are still traveling at the speed of the fall until they crash into the pelvic floor.
It's like holding a really heavy water balloon in a plummeting elevator that suddenly hits the ground floor.
Oh, that's a perfect way to visualize it.
The elevator stops instantly, but the water inside that balloon violently slams downward, stretching the rubber to its absolute limit.
Okay, let's unpack this, because how does the tissue physically handle that?
Well, consider the biological rubber catching that visceral slam. The pelvic floor muscles actually have a surprisingly small cross-sectional thickness.
They're pretty thin. Incredibly thin, especially when you compare them to the dense, heavy mass of the organs they suddenly have to decelerate. The sheer physics of that momentum transfer generates an enormous amount of downward force focused on a very small surface area.
So if the force is that violent, standard muscle tissue alone isn't going to cut it, right?
Not a chance.
Yeah.
The physics basically demands something structurally stronger to prevent complete system failure. Which brings us to the actual connective tissues doing the heavy lifting here.
Right, we're talking about two very specific tendon-like structures supporting the organs.
Yes. The arcus tendineus fascia pelvis, which we'll just call the ATFP, and the arcus tendineus levator ani, the ATLA.
The unsung heroes of human locomotion.
Truly. And they have very different biological makeups because they serve completely different mechanical purposes. So the ATFP is fundamentally a static suspensory structure.
Meaning it doesn't move much.
Right. It is highly concentrated in type I collagen, making up about, 85 to 90% of its collagen profile.
And type I collagen is the really stiff stuff, right?
Exactly. It's dense, stiff, fibrous. It's biologically engineered to resist sustained tensile loads. It acts as a rigid anchor attaching the fascia to the pelvic sidewall, so your internal anatomy doesn't just drop due to baseline gravity.
Okay, so the ATFP is the stiff, heavy-duty anchor. But if the whole pelvic floor needs to absorb a shock wave and bounce back, you can't just have stiff anchors.
No, you just tear something immediately.
Right. So where does the elasticity come from to handle the actual movement?
That is where the ATLA comes in. Its molecular architecture is completely different from the ATFP. The ATLA contains a much higher concentration of elastin and proteoglycans.
Which makes it stretchy.
Highly extensible and dynamic, yes. It physically has to stretch to accommodate the downward movement of the pelvic floor and, transmit the forces of the surrounding muscles contracting.
So wait, are we basically talking about two different types of bungee cords here? Like one stiff and one stretchy?
That's actually a really good analogy, yeah.
But if they stretch too far, do they snap back or do they stay stretched out? Because if these internal bungee cords take on a mechanical load that exceeds their physical tolerance during that massive elevator slam, what happens?
Well, that brings us to the critical distinction between synthetic materials and living biology. When a rubber band stretches too far, it might just stay permanently saggy.
Right.
But when these biological connective tissues experience overload, they suffer microscopic damage, literally micro tears.
Oh, wow. But isn't that just a normal biological repair process? Like when you're lifting heavy weights?
It initiates a repair process, sure, but the implications for fascial tissue are far more precarious than for your biceps.
Why is that?
Because if these tendon-like arches are stressed too intensely or they're forced to absorb those visceral slams too frequently without adequate recovery time, the cellular repair process just derails completely.
Like it can't keep up.
Exactly. The fibroblasts, the cells responsible for synthesizing collagen, they just get overwhelmed. And this leads to what we call maladaptive remodeling.
Maladaptive remodeling. That sounds bad.
It is. The tissue actively breaks down. The delicate balance of those collagen subtypes gets altered, and the extracellular matrix loses its normal, organized architecture.
So it's less like a rubber band stretching out and more like a thick rope where the individual structural threads are actually snapping.
Yes. And the body frantically tries to patch those frayed spots, but it heals improperly.
Leaving the entire rope fundamentally weaker, right?
Exactly. It progressively loses its mechanical integrity and becomes more prone to stretching out under less and less weight.
Which brings us directly to the inherent danger of repetitive impact. Because, a single 30-centimeter box drop might cause minor micro damage that a healthy body easily repairs.
Sure.
But what happens during a highly repetitive landing sport? Like distance running or gymnastics or, trampolining.
Right, because in high-impact sports, the pelvic floor muscles are forced to reflexively contract and relax with every single foot strike. It acts like an inner trampoline.
You hit the pavement, the trampoline catches the organs, bounces back, and gets ready for the next step.
But if you're running a 10K, that trampoline is catching thousands of consecutive visceral slams. And biological trampolines have a limit.
I'm assuming that limit has a name.
It does. Biomechanical research highlights a concept known as the continence threshold.
The continence threshold. Okay.
This represents the specific volume of repetitive impacts the pelvic floor muscles can withstand before their fast-twitch muscle fibers simply fatigue.
And when those fast-twitch muscle fibers fatigue, they stop acting like a bouncy, shock-absorbing net.
The moment those muscles tap out, they leave the structural connective tissues, our ATFP and ATLA, completely exposed.
Oh, man. So the muscles fail, and the literal ligaments have to hold the entire dropping weight of the internal organs.
Yep. They take the absolute brunt of the stretching force. This is the exact window when that maladaptive stretching rapidly accelerates, which frequently leads to stress, urinary incontinence, or eventually pelvic organ prolapse.
Wait, let me challenge this premise for a second.
Sure, go ahead.
Based on how the rest of the body works, right? Mechanical loading generally stimulates collagen synthesis. Like physical therapy relies on loading tendons to make them thicker and stronger.
That's true.
So shouldn't repetitive jumping act like weightlifting for your pelvic floor? Shouldn't all this running and bouncing trigger an adaptation that makes those structural tissues stronger, not weaker?
If we connect this to the bigger picture, it really comes down to the critical threshold between systemic adaptation and system failure.
Okay, meaning what exactly?
Well, you are correct that controlled progressive mechanical loading aligns collagen fibers and strengthens tissue. But in high impact, high volume sports, the sheer velocity and repetitive volume of those ground reaction forces, it frequently outpaces the tissue's biological rate of recovery.
Ah, so the micro damage is accumulating faster than the fibroblasts can lay down new organized collagen.
Yes, you push past that continence threshold, the muscles fatigue, the ligaments take the unmitigated load, the micro tears stack up, and the biological environment shifts from healthy strength building adaptation to chronic inflammatory overload.
So a movement that could have been a strengthening stimulus crosses a line and becomes a tissue-degrading event.
Exactly. And, there is another variable in this kinetic chain that's fascinating, and it has to do with foot arch flexibility.
Oh yeah, this completely caught me off guard in the research. Elite athletes with decreased foot flexibility actually have a noticeably higher association with urinary incontinence.
It's wild, but it perfectly illustrates how deeply interconnected our body's shock absorption systems really are.
Because if a runner has stiff feet or rigid arches, they can't absorb the initial ground impact forces efficiently.
Right. And that force doesn't just disappear. The shockwave essentially bypasses the foot, travels straight up the kinetic chain, and violently slams directly into the pelvic floor.
If your foot fails to act as the first line of shock absorption, your pelvic connective tissues are forced to do the job.
Exactly. But here is the really wild part. This entire system isn't fixed.
Right.
We tend to think of our anatomy as a set structure, but a woman's vulnerability to this structural stretching fluctuates based entirely on her biology.
The hormonal environment actually changes the material properties of the tissue itself.
Yes, and this is one of the most vital yet frequently overlooked aspects of biomechanics. Estrogen and progesterone are not merely reproductive hormones.
Right, because there are specific receptors for these hormones located throughout the musculoskeletal connective tissue matrix.
Including the pelvic floor and the suspensory ligaments anchoring it. The data clearly shows that during different phases of the menstrual cycle, like around ovulation and the luteal phase, the stiffness of that connective tissue demonstrably changes.
So hormonal fluctuations physically alter joint and ligament laxity on a week-to-week basis.
Absolutely. And that mechanism becomes profoundly amplified during the peripartum period, throughout pregnancy and postpartum.
Because the body releases high levels of hormones like relaxin and estrogen, specifically to soften the tissue matrix.
Right, making it extensible enough to survive the extreme mechanical stretching of childbirth.
But, why actively break down its own structural collagen? That sounds counterproductive.
Well, because the body have to allow a human head to pass through an otherwise rigid pelvic ring. To achieve that, it essentially has to temporarily dismantle its own structural integrity.
And it does this chemically, which is just fascinating. Our sources highlight that relaxin actually activates specific enzymes, matrix metalloproteinases, known as MMP1, MMP2, and MMP9.
Yes, and those enzymes are biologically designed to degrade collagen.
They're acting like microscopic scissors, intentionally snipping away at the molecular bonds of your internal hammock so it can stretch without catastrophically tearing.
Which is incredible, but that profound chemically induced laxity doesn't just vanish the moment the baby is born.
Right, the tissues remain altered, soft, and vulnerable for months postpartum as the hormonal levels slowly normalize.
And we also see the effects of systemic hormonal shifts at the other end of the spectrum. During menopause, the drastic decrease in estrogen fundamentally impairs tissue elasticity, weakening the pelvic floor muscles and structural supports even further.
Okay, here's where it gets really interesting for you listening.
Huh.
To translate this, your internal hammock is actively chemically changing its stiffness and tensile strength from week to week, or from life stage to life stage.
Yes.
You could do the exact same 30-centimeter box drop on a Tuesday and experience a completely different level of internal tissue stretch than you would doing that exact same jump 2 weeks later.
Because the mechanical load of the jump remains identical, but the biological tolerance of the tissue catching that load has fundamentally shifted.
Oh.
A connective tissue bathed in relaxin and collagen-degrading enzymes is going to suffer microdamage at a vastly lower impact threshold than a tissue in a standard hormonal state.
That reality completely reframes how we should think about training and impact management.
It has to.
Because we obviously cannot turn off gravity. And the scientific consensus is overwhelmingly clear that we shouldn't stop exercising The systemic benefits of physical activity far outweigh the risks of being sedentary.
Oh, absolutely.
So how do we mitigate this? How do we protect these vulnerable tissues from maladaptive stretching when we want to run or jump or lift?
This is where we integrate biomechanics and specialized physical therapy, because the objective isn't to cease movement. The objective is to proactively manage the intra-abdominal pressure and train the neuromuscular system to absorb shock efficiently.
And one of the primary evidence-based techniques recommended for this is called the knack,
Yes, the knack.
which sounds incredibly simple, but the mechanics behind it are brilliant. It's essentially a conscious, timed pre-contraction.
Right. You intentionally engage and brace your pelvic floor muscles a split second before and during an impact.
Like right before your foot hits the ground, or right before you sneeze.
Exactly. But the brilliance of the knack lies in how it alters the tension of the ATLA, that dynamic connective tissue we talked about. By pre-contracting the muscles, you are essentially pre-stiffening that connective cord.
You eliminate the slack in the system before the visceral slam hits.
Exactly. Instead of the organs dropping and causing a violent snapping stretch on relaxed ligaments, the entire system is already braced to decelerate the load smoothly.
And breathing mechanics play an equally massive role in this pressure management, right? Like, if you are out for a run right now while listening to this, check your breathing.
It's so important.
Are you chest breathing and pulling your diaphragm up, or are you actually utilizing diaphragmatic breathing? Because researchers describe the core pressure system like a balloon.
It's a great visual.
You have the diaphragm on the top, the abdominals wrapping the sides, and the pelvic floor sitting at the bottom.
Right, and proper diaphragmatic breathing is the ultimate pressure regulator. When you inhale deeply into your belly, the diaphragm physically pushes down.
And for the pressure inside that abdominal balloon to remain stable, the pelvic floor at the bottom must naturally descend and relax to make room for the organs shifting downward.
Yes.
But wait, if someone is already dealing with a tight, hypertonic pelvic floor, maybe they're chronically stressed or they've been doing a ton of heavy lifting without proper mobility work, doesn't practicing pre-contractions and constantly keeping the core tight just make it worse?
That highlights a major biomechanical misconception. A muscle that is stuck in a state of constant hypertonic contraction is practically useless for shock absorption.
Because it's already tight.
Right. It cannot be truly strong if it cannot relax.
It's like a trampoline that has zero bounce left because the springs are already pulled as tight as they can possibly go.
Exactly. And if a bowling ball drops onto a fully stretched, rigid trampoline, the springs just snap.
Wow.
That's the core of the issue. Neuromuscular control is just as important as brute tissue strength. The tissue must be able to stretch, yield, and rebound dynamically to manage kinetic energy.
That makes total sense.
Which is precisely why the relaxation phase of diaphragmatic breathing is just as crucial as the contraction phase. If your pelvic floor is in chronic spasm, it cannot dynamically catch the organs during a run.
The muscles fail to yield, which means the structural ligaments take all the microscopic damage.
Exactly.
So beyond breathing and pre-contracting, what can we physically change about the way we move through space? Because there's some incredibly practical biomechanical advice in our sources regarding running mechanics.
Yes. One of the most immediately effective mechanical adjustments a runner can make is increasing their cadence, their step rate.
The biomechanical data strongly suggests aiming for around 170 to 180 steps per minute.
Which feels like a rapid patter of tiny steps if you are used to long, loping strides.
It definitely takes some getting used to. But what is the actual physics behind why shorter strides protect the pelvic floor?
It all comes down to vertical oscillation. When you take long strides, you launch your center of mass higher into the air.
And more airtime equals a larger vertical drop, right? Giving gravity more time to accelerate your body weight.
Exactly. By taking shorter, quicker steps at a higher cadence, you drastically reduce your vertical oscillation. You stay closer to the ground, which mathematically reduces the momentum transferring to your abdominal viscera upon landing.
You're literally altering the physics of the visceral slam.
You're shrinking the height of the elevator shaft before the crash.
That's brilliant.
Oh.
And alongside cadence, they emphasize focusing on soft landings, trying to run quietly.
Yes. Running quietly naturally prompts your neuromuscular system to absorb shock through the flexion of the knees and hips, rather than just locking out and sending that shock wave straight up the kinetic chain into the core.
But what's equally important is activity modification when the system gives you warning signs.
Crucial.
If you're experiencing leaking during a run or a jump,
Hmm.
which is the ultimate undeniable physiological sign that you have breached your continence threshold. You cannot just push through it.
No, absolutely not. Pushing through it is exactly how you turn temporary muscle fatigue into permanent maladaptive remodeling of the ligaments. If your pelvic floor muscles are fatigued and failing to fire, you have to swap the highly repetitive, high-impact movements for low-impact alternatives.
You pivot to cycling, swimming, or maybe modified Pilates.
Exactly. You maintain your cardiovascular and muscular fitness while giving the overstretched connective tissues the vital recovery time they need to rebuild their collagen architecture.
So what does this all mean? We have covered a massive amount of physiological ground today.
We really have.
We started by visualizing the raw physics of a landing, how gravity, acceleration, and momentum hurl our internal organs downward against the pelvic floor in a microscopic visceral slam.
We explored the molecular architecture of the tissues forced to catch that weight, right? Contrasting the stiff, supportive anchor of the ATFP with the dynamic elastic transmission of the ATLA.
And learn precisely how mechanical overload forces them to break down and remodel poorly.
Yes.
We looked at the inherent danger of breaching our continence threshold during repetitive sports, where fatigued muscles leave our connective tissues completely defenseless.
And we unpacked the wild reality that shifting hormones chemically alter the physical stiffness of our internal shock absorbers.
And finally, we detailed the biomechanical strategies, like utilizing the neck, mastering diaphragmatic breathing, and increasing running cadence to reduce vertical oscillation that can actually actively mitigate the damage.
It is a remarkable, highly evolved system of dynamic load management. But, before we go, I want to leave you with a broader evolutionary thought to mull over.
Oh, I like where this is going.
We've established today that our internal connective tissues are constantly breaking down and remodeling based on the precise physical loads we subject them to on a daily basis.
The body ruthlessly adapts to whatever environment or stimulus we provide it.
It does. But consider the lifestyle of the modern human. For hundreds of thousands of years, human movement was characterized by constant, varied, moderate-level activity.
Walking, foraging, carrying things.
Exactly. Today, we've engineered an environment that swings wildly between two extreme poles,
Sitting entirely sedentary at a desk for 40 hours a week.
followed by highly intense, high-impact weekend warrior workouts, heavy lifting, or extreme cross-training classes.
So we go from zero mechanical load to absolute maximum mechanical load in the span of an hour.
Right. So given how intimately our internal fascia and pelvic ligaments remodel in response to daily sustained loading, how might these extreme, unnatural swings in modern fitness habits be permanently, structurally reshaping the internal anatomy of modern humans compared to our ancestors?
Wow.
By bouncing between extreme sedentary behavior and extreme impact, are we inadvertently building internal structures that simply aren't engineered to support the way we currently choose to live?
That is an incredibly provocative question to end on, and it really changes how you look at a simple gym routine.
It definitely makes you think.
Next time you jump off that step or your foot strikes the pavement during a jog, take a second to think about the complex, brilliant, and sometimes vulnerable fascial hammock working overtime inside you to catch the fall. Keep learning, keep moving, and we will catch you on the next deep dive.